In chapter 3, we are finally getting into the very core of pure math 1. This is, for me, the most important chapter of all of them because this introduces you to the realm of calculus. Okay? And it actually starts with something that you already learned a long time ago. Okay? So, let's start with this. You know this for a long time. How do you calculate the gradient of a straight line? You already know this. If you have the line written in the form y equals mx plus 2, the gradient is right here. It is the coefficient of x. All right? If you don't, and if you know the coordinate of 2 points from that line, you know for a long time as well, we actually talked about this in chapter 1, that you can calculate the value of m doing the difference in the y coordinates divided by the difference in the x coordinates. In this case, this would be 2. But what if you have something that is not a straight line? What if you have a curve? What is going to be the gradient of a point in that curve? At first glance, it doesn't make sense, right? Because if you have a curve, then by nature, you don't have a straight line from which you can get the gradient. But you already know, also for quite a long time, that you can calculate or estimate, at least until now, the value of the gradient of a point in that curve by doing something that is called a tangent. What is a tangent? Well, if you have here, I have drawn here for this particular curve, which is the simplest parabola that you have, the simplest quadratic, the x squared, which are drawn here in blue. You can get the gradient on this point over here, in this case it was 0.5, x equals 0.5, by drawing a tangent. And then, once you have a tangent, and the tangent is a straight line, you can get any 2 points from that tangent and calculate the gradient. But there is a problem with this method. And the problem is obviously that two different people would draw slightly two different tangents, right? And that's assuming that you have access to the curve, to the graph of the curve in the first place. All right? So we need a method that allows us to calculate the gradient of a point belonging to a curve that is irrespective of the fact that you may or may not have access to the sketching or the drawing of the function itself, and is not dependent on the ability of people to draw tangents. All right? And this is what this whole chapter is about. So how are we going to do this? I'm going to use this example, all right? And then you can generalize for any other example. Actually, I'm going to do that later on. So we're starting with this parabola x squared. And the main point is what is the gradient of the curve on this specific point. And the point that I chose, quite randomly, was the point 0.5, 0.25. Okay? So if you plug here on x 0.5 and if you square it, you have the y coordinate 0.25. It is right here. So I've drawn here already the sketching of the tangent, and I want to get the exact value, not dependent on the ability of people to draw the line. I want the exact value of the gradient on that point. And then by extension, for any other point of this parabola, and extension of that, the gradient of any other point on any other curve. All right? So stick with me to look at this method. What is the main concept behind this? If we want the gradient on this point, we can start by getting a chord, and you know what is a chord? It's a straight line that cuts the curve in two different points, one of which is passing over the point that you are looking and that you are studying, in this case, the 0.5, 0.25. Quite randomly, I picked this chord over here that passes on this point, and that one over there that is arbitrarily close to the one that we are studying, and this was point 0.7, 0.49. Okay? So I picked these 2 points. Okay? I drawn here the chord, and this is the yellow line that you can see here, right? And as you can see, the gradient of this one is not exactly the one that we want, but it's close enough. So let's calculate the gradient of this chord. Now we know the coordinates of the points, so we can apply the formula that you know for a long time, and we got this gradient 1.2. We know just by inspection of the graph itself that this gradient is bigger than the one that we want. The one that we want, the one sketched here in blue, is slightly smaller. Don't forget the gradient is the inclination of the line. So what are we going to do to get closer to that? We are going to pick another point that is not going to be this one. It's going to be another one that is closer to the one that we want, the 0.5, 0.25. And that's what I did over here. Now I picked the point 0.6, 0.36. As you can see, it's getting closer to this one, right? And then I apply the same formula. If I apply that formula, I get this gradient over here, 1.1. It's getting, I didn't bother to sketch this one, otherwise it would be too confusing, but the gradient of the second chord is going to be smaller, right? So I'm going to keep bringing the second point closer to this one. So the third point that I picked was 0.51, 0.2601. Again, we are going to use the formula for the gradient to calculate the gradient of this chord, and we are getting to 0.01. See, this is getting down and down and down, and then the last point that I picked, it was 0.501, and this will give this y coordinate for this point. I use the formula for the gradient again, and now I have a gradient of 0.001. So look at what's happening. I started with a gradient of 1.2, and as I bring the second point closer to the one that I'm studying, the gradient is getting down, and apparently is getting closer to what? It's getting closer to 1. So it seems that the gradient of the line that we want, the tangent on that point, is going to be 1, but we need a way to actually prove it and be 100% sure. So what do we do? And this is the method that is valid for any other function, not only this one, but any other. I'm going to use it for this one though, okay? So we are going to have the point x, we are going to have the point with coordinate x and y, and then I'm going to express the distance that goes from the point that we are studying, the one with coordinates x, y, and to the other one that is arbitrarily close to it as delta x and delta y. Now, what is this delta? You can see that this is a lowercase delta, the letter that is usually represented in math to express difference. But this is a lowercase delta, meaning that this change is very, very, very small. This is actually very, very close. This value is so small that it's actually very close to this, but still it exists, all right? So the increment in x is called delta x, and the increment in y is going to be the delta y, okay? And as this gets smaller, the gradient of the chord gets closer to 1, as we saw over there. So if we take the general point x, f of x, so in this case the point was 0.5, 0.25, the value q, the one that is close to point P, is going to be what? Is going to be x plus that small increment and f of this, all right? Don't forget what we are talking about. What is this f of x? This is just the outcome of substituting x in the function. So in this case, the function was x squared. If I substitute 0.5 on x squared, I will have 0.25 squared, and this is the result, okay? So that's what this means. Don't get alarmed by the notation. This is actually very simple, all right? So this is x and the outcome of substituting x in the function. And this is the other point, which is x plus the little bit and f of that point, okay? So what is going to be the value m? This is just a formula that you know for a long time for the gradient. It is this minus this divided by this minus this. Okay? In this particular case, then here I'm going back to this particular function, which is x squared. What is this? I'm going to start with this one. F of x is x squared. What is f of x plus delta x? Is x plus delta x squared. You already learned about composite functions, so this is x plus delta x squared. Then I am just going to expand this, and this is what you get, all right? Underneath what you have, before I move on with the numerator, I'm going to look at the denominator. So I'm going to have this bit minus this, so x plus delta x minus x is just delta x, all right? Okay, so going back to the numerator, I expanded these brackets, okay? And I have here x squared and there minus x squared, so these two cut out. And then I can separate what is left, which is this bit, into different fractions. So 2x delta x divided by delta x plus delta x squared divided by delta x. And then I can cut out things that can be cut out, namely on the first fraction, the delta x, and this is going to yield just 2x. And over here, I can cut that square with this delta x, yielding just delta x. Okay, so what is this again? Don't forget what we are doing. This is an expression that allows us to calculate the gradient of the function x squared at any point. All right? And what is the main concept again of this delta x? This is a value that is very, very, very close to the value x. So what happens if this tends to 0? That's what was happening over here. The delta x is started as being 0.2, then the delta x over here was 0.1, then it was 0.01, then it was 0.001. It tends to 0, right? You represent this mathematically like this. The delta x, this distance from the point that you are studying, tends to 0. So if this tends to 0, eventually you can disregard it altogether. This is going to be 10 to 0, so you are left with what? You are left just with 2x. What is this 2x? Again, this is an expression that allows you to calculate the gradient on every single point of this function, the x squared. So on the point that we are studying, which is point 0.5, what is going to be the gradient? Well, just substitute on this function. Don't forget, this is a new function, if you look at it. Just substitute x by the point that you are studying, which is 0.5. Then you have 2 times 0.5, 1. So you have proven beyond any doubt that the gradient of the function x squared on point 0.5 is 1. A little while ago, it seemed that it was tending to 1, but now you have proven it. More than that, you have proven, or you have figured out a way to calculate the gradient on any point of the function. If you just substitute x by whatever point that you want, you will get the gradient on that point. I'm going to show that in a bit. Just for you to know, not that you are going to use this much in pure math, but the way to represent this is like this. To represent the gradient, the expression to get the gradient is like this. The limit as delta x tend to 0 of delta y over delta x. You are not going to see this many times though, all right? You are going to see what? You are going to see any of these expressions. All of these, in this particular case, the function is x squared, so you can see it as dx squared over dx, or dy over dx, this is more general for whatever function y, or y dashed, okay, this is very common, or f dash of x. All of these mean the same, okay? So don't get alarmed if you see these all mean the same. You are getting the expression for all gradients. This is the derivative of the original function f of x or the original function y, all right? They all mean the same. In this particular case, when the function is x squared, the expression is this, 2x. This expression gives us then the gradient of the parabola x squared at any point x, and this itself a function. All right, as you can see, 2x, it is a function, but is a function that relates to the original one, in this case the x squared, and this function allows us to calculate the gradient on every single point of the original function. All you have to do is to substitute x by the point that you want, and you get the gradient on that point. Look over here. I have drawn here the original function x squared. This is the blue line, the parabola, okay? Then I just put these random points, minus 2, x equals minus 2, minus 1, 0, 1, and 2. So the y coordinate is going to be all of these over here. Then I've just written on this column the expression for all the derivatives. And now see what this means, what this is actually. When x equals minus 2, the y is 4, so we are talking about this point over here. What's going to happen if I substitute x by minus 2? I have 2 times minus 2, that's minus 4. And what is this? This is the gradient of the original function on point minus 2, 4. As you can see here by this line and here by the pen, it is this inclination, minus 4, right? If I do the same thing, but now for point minus 1, 1, this point over here, and if I substitute x by minus 1, I have the value minus 2. What is minus 2? It is the gradient on point minus 1, 1. If I now substitute x by 0, I have 0. It is this line, okay? You have 0 inclination. More on these points in a bit. Our next lesson. In point 1, I will have the gradient 2. In point 2, I will have the gradient 4. See, what is happening to the gradient of the function? It starts as a huge negative number, is getting less negative, closer and closer to 0. On point x is 0, and then starts increasing. All you have to do to figure out the gradient on any single point is substituting x by that point, by the x coordinate of that point, and you have the gradient on that point. This is what it means. And this itself is a function, 2x, represented here by this yellow-orange line, okay? You have the original function in blue, the x squared, and you have the second function, the function of the derivatives, which is this straight line over here in yellow. Make sense? Now, you may think at this point, well, it's all very interesting, but figuring out the value of the gradient using the method that I explained before seems so complicated, and it actually is. There is a very, very straightforward method that it is the one that you are actually going to use. So I try to explain it over here. I've put here on the first line the value of the gradient of the function that we used, okay? I actually explained how to get this a little while ago. But what if you have a function that is ax squared, in which way a is a constant? For example, 4x squared. What would be the expression for the gradients? Well, in that case, it would be 2ax. What if it was just x, the straight line, y equals x? In that case, the gradient, it would be 1. You know this for a long time, right? This is a straight line, the gradient is 1. What if y is a number, okay, is a constant? Then the gradient is 0. You know that for a long time. What if it is 4x? Then the gradient is 4. All of these 3, actually not 2, but 3, you know for a long time. But what if you have a cubic? Let's say that you have 4x to the power of 3, 4x cubed. Then the gradient, the expression for the gradient is going to be 3 times 4x squared. Are you following the trend? How are you getting from what you have here on the left to what you have here on the right? In other words, what if you have ax to the power of n, in which a is a constant and n is also a constant, a number? Then the gradient is going to be n, whatever n might be, times a, whatever a might be, times x to the power of n minus 1. Take this as an example. So my example was 4x cubed. So the expression for the gradient is going to be 3 times 4, which will be 12, x to the power of 3 minus 1, which is 2. Okay? This general way of getting the gradient is the one that you are actually going to use, and this can be used for whichever value of n that you can think here. An integer, a fraction, a negative number, etc. The process of finding a function f dash of x that gives us the gradients of the tangents to a function f of x is called the differentiation of f of x. We are getting small differences that allows us to calculate the gradient, hence the name differentiation. All right? The gradients of the tangents to a function are extremely important to the study of that function, as they measure the rate at which y changes in relation to x at any point. If you go back to this function, you can see just by looking at the gradient of the function that the rate at which the function is changing is much higher on this point than on this point. See, it's a parabola, so the bigger the value of x, the more rapidly the value of y is changing. This is given by the value of its gradient. I believe this is all for lesson 1. So we are going to see how to use differentiation next lesson. For the time being, and on the questions that you have later, the important thing is that you learn how to practice how to differentiate functions as fast as possible, because the main idea beyond you learning this is that you learn how to use this new tool to answer more complex questions. All right, so right now just go ahead and practice differentiation using this method, using this generalization over here, and do it very fast. You are not going to be tested on your ability to differentiate. You are going to be tested in your ability to understand and use differentiation to answer a broader range of questions.